Hello, today we are going to talk about how to calculate molecular orbitals of heteronuclear diatomic molecules. Before the calculation, I will explain some concepts for the calculations. First is Born-Oppenheimer approximation. The Born-Oppenheimer approximation allows us to select an internuclear separation in a diatomic molecule and then to solve the Schrödinger equation for the electrons at that nuclear separation. Then, we choose a different separation and repeat the calculation, and so on. In this way, we can explore how the energy of the molecule varies with bond length and obtain a molecular potential energy curve like this. Second, we should compare the electronegativity. The electronegativity is a parameter introduced by Linus Pauling as a measure of the power of an atom to attract electrons to itself when it is a part of a compound. Pauling used valence bond arguments to suggest an appropriate numerical scale of electronegativities could be defined in terms of bond dissociation energies d0, and proposed that the difference in electronegativities could be expressed as this equation. And these are examples of Pauling electronegativities. Lastly, variation principle provides linear combination to discuss bond polarity and to find the coefficients used to build molecular orbitals. This is the definition of variation principle. If an arbitrary wave function is used to calculate the energy, the value calculated is never less than the true energy. This principle is the basis of all modern molecular structure calculations. The principle implies that if we vary the coefficients in the trial wave function until the lowest energy is achieved, then those coefficients will be the best. The method to calculate the molecular orbitals can be illustrated by trial wave function. We show in the following justification that the coefficients are given by the solution of the two secular equations. The parameter alpha is called the Coulomb integral. It is a negative and can be interpreted as the energy of the electron when it occupies A or B. In a homonuclear diatomic molecule, alpha A is the same as alpha B. The parameter beta is called the resonance integral. It vanishes when the orbitals do not overlap, and equilibrium bond length it is normally negative.
We can get the wave function and the energy using variation theorem. If we know the Coulomb integral, resonance integral, and overlap integral, we can calculate the coefficient of the wave function and the energy. First, take trial wave function like this. The expectation value can be expressed by the operator. The operator of the energy is Hamiltonian, so the energy can be expressed like this. Specific coefficients in the trial function that minimize the energy is the seeking coefficient of the wave function of MO because of the variation theorem, so the differential value is 0. Then calculate the numerator and the denominator and simplify it. We can now differentiate the energy and two equation appears. Use secular determinant to solve the equation and solve quadratic equation for energy. Therefore, the energy can be calculated by the formula. Plus, use normalization of the wave function and upper part of the secular equation. Then, the formula to calculate the coefficients of the wave function can be shown. By using the wave function and the energy of the MO, we can get molecular orbital energy level diagram. In the MO energy level diagram, HOMO, highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital, are the important factors. As you can see in the example diagram of HF, HOMO is 2px and 2py, while LUMO is sigma star. Let's see the usage of HOMO and LUMO. First, we can know the color of the molecule. The light energy absorbed or emitted when the electron moves between HOMO and LUMO. The energy difference between HOMO and LUMO induces specific frequency of the light, so we can know the type of light. For example, H2 has the energy difference of 258 kilocalorie per joule, which is the range of UV light. So H2 has no color. If the energy difference is in the range of visible light, then the molecule can have certain color. Second, we can know the chemical reactivity. The electron pair in the HOMO can act as a nucleophile because those electrons are in the highest of energy state which can easily donate to others. First type is electron pair in the non-bonding MO. Lone pair electrons are used to form new bonds, so no bond breaks. The result of the reaction is this. Second type is electron pair in the pi bonding MO. Pi bond breaks and use those electrons for forming new bond. The result of the reaction is like this. Third type is electron pair in the sigma bonding MO. Sigma bond breaks and those electrons for forming new bond. The result of the reaction is this. However, the electron pair in the LUMO can act as an electrophile because those empty orbitals are in the lowest energy state, which can easily receive from others. First type is empty orbitals in the non-bonding MO. No bond breaks when the new bond is formed. The result of the reaction is this. Second type is empty orbitals in the pi antibonding MO. Pi bond breaks because of the compensation of pi antibonding and pi bonding MO, and new bond is formed. The result of the reaction is this. Third type is empty orbitals in the sigma antibonding MO. Sigma bond breaks because of the compensation of sigma antibonding and sigma bonding MO, and new bond is formed. The result of the reaction is this.